So I brought something with me today. This little guy here, this is Pete. Pete is a forensic investigator for an insurance company. And he has a case to solve. And I also brought the case with me, kind of symbolic right here. This is a small vehicle, and we can see it's clearly damaged. And what is going to happen today is, together with Pete, we will solve an automotive forensics case. Because Pete asked for help, obviously. And we are the experts. So let's dive deep into it. But before we start, we need some fundamentals to work with. So let's start with automotive fundamentals to begin with. So in general, vehicles are complex systems. They introduce different components. Some are listed here. So some examples are, for example, the telematics control unit, which is responsible for communicating with outside services. Another example, if we just pick out one, is the infotainment system. Infotainment system is the most present one for interconnections between the vehicle and the passengers, for example, because you connect your smartphone with the infotainment system. Pretty interesting too, and let's say a perspective out of a forensic perspective, is the immobilizer system. In Germany, we call it the Wegfahrsperre. It means that something that is responsible to acknowledge that everything within the car is working fine, especially the key, that it's the right key, and to not allow to steal the vehicle that easy. Another example are gateways. Gateways are intermediate system between different bus systems. So if, let's say, I have a LIN bus and a CAN bus, and information needs to be transferred for a device from the LIN bus or through the LIN bus through a gateway to the CAN bus to another device, the gateway is responsible for translating the communication between both devices and within both of the bus systems, the communication systems. Another example is the airbag. Airbag control units are pretty obvious. If you have a crash, the airbag pops up and the crash needs to be pre-sensed. And also there's some predefined events or data that is collected from the airbag control unit up to 5 seconds before the event occurs. Another pretty interesting example for automotive systems in case of automotive forensics is the outside world, so the vehicle ecosystem. Examples are car to X, so car to something else, car to infrastructure, like traffic light systems. This is pretty interesting in forensic cases too, because those systems might store relevant information. Smartphones or smart phones are also interesting example of the vehicle ecosystem, because those devices can hold traces which are relevant in investigations too. Another pretty interesting example is the backend services. So all the connection from the telematics control unit to the backend is done through the telematics control unit, and then you have predefined information which is stored within the backend of the manufacturer. So I just showed two examples of in-vehicle components and ecosystem components, but what we can clearly see right now is that vehicles are pretty complicated systems. Those are very complex. And this picture here is just hardware components. There's no view on the software, obviously. So from a software perspective, vehicles are very, very, very complex too. So it's very hard to predefine all the relevant technologies, data assets, communication systems, data storage systems, and so on. So it's a pretty hard task for Pete to perform forensic analysis on a modern vehicle. What we also need in order to perform such investigations are digital forensic fundamentals. In digital forensic, you basically have one main goal. That's the reconstruction of events. Everything is based around this main goal. So if something happened, no matter what the assets are, so if it's a vehicle or a laptop or a smartphone, and then your goal as an investigator is to reconstruct what happened actually, because you weren't on site, obviously. Then you consume all the information and you try to reconstruct it. In general, there are 5 separate steps. It depends on how deep you want to go into the different steps, but in general, you can say there are 5 separated steps. First one is forensic readiness. This is where you define what is actually required to perform forensic investigations. Because obviously, if there's no data, you can't perform forensic analysis or digital forensic analysis. Step 2 is extraction. This is where you actually collect the information from the different assets. This can be done through specific tools. There are some forensic tools that you can use, but there are also common utilities like the DD utility in Unix systems, which allows us to extract the information in a specific format. The third phase is the analysis phase. This is where you have collected the information, then you dive into it. So you analyze it. What is this specific byte string or bytes are representing? What could this string mean? There are some hexadecimal codes. What do they represent? And all this analysis is also done using tools or using manual reviews from experts. Phase 4 is the interpretation. There you have a lot of connected evidence, a lot of devices. You analyze, you extract it, and then you try to connect the dots. So you interpret what could have happened. So what is the evidence trail? So reconstruction of event. That's where we came up with the goal at the beginning. And the last step is reporting. There's where you start your report, what you actually did, why you did it, how you did it, that people can understand it and are able to reproduce the results you presented. Reporting is pretty interesting because you can either report internally or document it internally for yourself, but sometimes in forensic investigations you need reporting for court. This is where reporting is pretty complex and interesting because there you have to look at a lot or determine a lot of why is this step really relevant? Did you, for example, manipulate any evidence by extracting the evidence? And this is pretty interesting for court-related reporting. And why is even automotive digital forensic possible? Or forensics in general? Well, it's based on Locard's law from Dr. Edmund Locard back in 1934. He stated that any action of an individual, and obviously the violent action constituting a crime, cannot occur without leaving a trace. And this also applies to digital systems. You can't do anything without leaving a trace. The trace might not be digitally too. It might be a physical trace. So there might be memory wear on a specific device on the system. So this is pretty good for us because we can already state that when something happened, we find trace. If it's easy to find a trace, no doubt, sometimes it's extremely hard. The main questions you're asking in forensic investigations can be categorized into 6 so-called W's, which is who, why, what, when, how, and where. Those are the general questions you ask to yourself in order to reconstruct some events. In some cases, you don't have all that, not answered all the questions, but you solve the case somewhat otherwise. So the main goal is obviously to always look on those questions and try to answer them one by one for reconstruction purposes. There are different domains or areas of research in digital forensics itself. So we have mobile forensics, which, for example, looks on smartphones. We have networks forensics, which is designed specifically for tools and processes, methodologies around network forensics, yeah. Cloud forensics, looking at the cloud. Computer forensics, looking at computer. IoT forensics, looking at IoT devices, so highly connected, small little devices. And there's also automotive forensics, which is interesting in our talk today. So let's dive right into the fundamentals for automotive digital forensics. The definition for automotive forensics presented by me is that we have implementation of technologies, processes, and also methodologies already known in the automotive domain, digital forensic science, to the automotive domain. So we get the stuff from which we already know that it's working from the digital forensic science and try to apply it to automotive systems. It's not only for getting all the stuff from the digital forensic science, it's also applying new interesting features, methods, technologies, which are then specific for the automotive domain, because automotive is a kind of specific area, because we have cyber physical systems, we have interconnected devices, we have highly complex systems. And this is where we're not only looking at in-vehicle components, so devices which are installed within the vehicle itself, we also look at components from the outside world, so the vehicle ecosystem. I presented it at the beginning, that's OBD dongles, for example, or the backend system, Car2X. This is also relevant in investigations. It's interesting because those devices can store data too, and we can correlate the results with the information we get from in-vehicle systems. At this year's DFWS, I presented a methodology or process which allows us to perform forensic investigations on modern vehicles. We have different phases in numbers, forensic readiness, data acquisition, analysis, and also documentation. Those are pretty similar to the general process I just showed you some minutes ago. But those are specific for the automotive domain, because in automotive you have different vehicles from different manufacturing years. And depending on the age, they introduce different technologies. So here's where forensic readiness comes into place, and acquisition also, where we need to determine if we can actually get information which is relevant in the case we want to solve. So let's say you have a very historical old vehicle. There isn't a lot of digital evidence within those devices compared, for example, to a brand new Tesla vehicle. What's also interesting is the data within vehicles. At this year's ESCA, I presented different data classes that are firmware, communication data, user data, safety data, and security data. And what we can do is we can look at different components installed within vehicles. This is a list I'm presenting here. And this list is also, and we can map the data classes onto the components to validate. Let's say if we really need security data, for example, then we have to look at battery-related systems, endpoint devices, telematics control units, infotainment, immobilizer, and gateways. But it's not that easy in automotive digital forensics. We have a lot of challenges we need to address. Specific challenges are data correlation, integrity, interpretation, collection, but also privacy and security. Some examples here. Let's say we have a normal vehicle, and they also introduce some proprietary tools. So tools that are designed from the manufacturer for manufacturer-related purposes or service-related purposes. For this technologies, you usually need specific tools, specific hardware, which is then connected to the vehicle to get the information. And this makes correlation, but also interpretation and also collection pretty hard, because you actually need those devices. And data interpretation is done on manufacturer side, so they have the documentation, not you as a forensic investigator. Data integrity is also pretty interesting because currently there's no law that determines that data within the vehicle needs to be integrity protected. So usually the data is not integrity protected, and how do you validate that the information you collect is actually true and you can use it? So now we collected some good fundamentals. We know general stuff about automotive, we know general stuff about digital forensics, and we know general stuff about automotive digital forensics. So I think that we are now able to help Pete with his case. So let's jump straight into the case. So in the case we will look at today, we are looking at a Tesla vehicle. So in the specific circumstance that has occurred, I can just present you this small story. It's that Pete got a call from a police officer. There was an accident. So he drove with his vehicle to the scenery and saw that something dropped down a hill. And he got to the officer, said, "Yeah, hey, I'm Pete, I'm the forensic investigator today. Do you called me to need your help? You need my help." So Pete is then presented with all the evidence they collected on a physical side. So a driver told them that the vehicle parked automatically, and then apparently it drove down the hill and the vehicle broke and the man got injured, the driver. So Pete said, "Okay, then I think I'll just collect some information from the vehicle system. We already have seen them in the fundamentals." So he checks where the vehicle is, but there is no vehicle anymore. So he asks the police officer, "Where's the vehicle? I can't do forensics or digital forensic or nothing." And this is where he got handed the airbag control unit. We can see a picture right here on the left-hand side, and his task now is to collect information only from this device, and this device is from the installed vehicle or the vehicle, the targeted vehicle. So I said, what could we do right here? Well, we can analyze the ECU, right? So there are some proprietary tools. We can see that's a Bosch ECU, so we can collect some information from those devices, right? Or we can install it into another Tesla and try to get information using another Tesla's interfaces. But sadly, we don't have access to another Tesla. So I guess we need to analyze it. So what we first can do is we can try to disassemble the ECU, check if everything is working fine, what we are actually dealing with, other data storages and so on. So Pete just opened it up together with us. And there we can see it. There's some damage on the vehicle, on the ECU itself. So what we can see here is some water damage on the device itself. So it looks like it's broken. And hopefully it's not broken. And not the data, all the data is lost. The question how the water got there isn't something we need to solve here. We are only here for the digital forensic perspective. We can state it in our report, and we need to state it, but this is not the case we are trying to solve right here. So how did the water got it in? So I state one question: what could we actually do right now? So what we can do is we can try to collect the information, for example, using Tesla's own EDR tool. There's another screenshot here, proprietary tools I told you before. This is something you can buy for a few, like 1,000 euros, 2,000 euros, and this allows us to collect the information. So we can try it, and when we tried it, it's not working. That's not good. So what we suspect right here is that the interface is broken. So something is not okay right here. So let's try to dissolve the storage devices, because if we dissolve the storage devices, we can maybe collect the information from the storage device itself, just pretty easily using, for example, an external adapter, which is also, for example, used in mobile forensics. Well, I showed you some challenges before, and one of them was interpretation. So if we just collect the data blob out of the flash storage, we don't know how to interpret the information. There is no available documentation how to interpret Tesla flash storage, which is installed on airbag ECUs. So that's not good. So are there any other options we could do? Well, we can, for example, extract the storage device and install it into another working airbag ECU. Because obviously, the main issue right here could be that the interfaces are not working anymore. And with another ECU, the interfaces are working. So let's try this out. This is where, for example, where memory forensics come into place, or embedded forensics, sorry. So we use a van to get off the chip, get it off, install it onto another device, and then we can try again with using the Tesla EDR tool. In this case, we need to be very, it's hard to break something, so it needs some tests, some skills. Usually you have some dummy boards before you actually approach the real target. So next step is we can collect information using airbag ECU, the CDR2 from Tesla. So now, awesome, it works. We get information. So in Tesla's EDR tool, you just plug it in right on the as we can see in the screenshot right here from another engineer bureau, and we collect the information using the tool, and then at the end you get presented with a JSON file. JSON file usually contains some hex dumps, which is not interpretable by you, but from the Tesla's perspective, they have a website where you can upload the JSON dump, and then you get an actual EDR report right afterwards. The report usually then shows you in PDF form what happened, the different tables, some information regarding the ECU and the different events that occurred. Awesome, so there's the website. So pretty easily just upload the file, submit it, and then we should get the information from Tesla about everything that was stored within the airbag ECU. But sadly, we get an internal error. And the main question here is, what could be the issue? Why is there a main error within that we get from the report or from the website? Okay, let's check back. So we got the storage device, installed a new component, and uploaded it pretty easily. So what could we expect what it's stored? It's something related to the device, I guess. So let's say the vehicle VIN, which is an identification number for the vehicle. And I think that maybe some checksums could be there too, and that was the case here. So obviously the chip from another device stores information for a specific vehicle which the device got installed, the airbag ECU, and the VIN is obviously different from the other airbag ECU we collected, so two different cars. So I guess that Tesla's website is also checking if the VIN is correct and maybe validating a checksum based on the VIN also. So we need to fix this too. So we need to manipulate somewhat the JSON file applied with a valid VIN and also with a valid corresponding checksum. Okay, let's go, right? But how I just got the info that we forgot something at the beginning. So we learned in the fundamentals that it's all about the different questions that are asked and to reconstruct the events. So we just dove straight into forensic analysis or extraction, right? Well, we obviously didn't got any forensic questions from the stakeholder. to reply, the police officer just gave Pete the airbag ECU and told him to do stuff, but not actually what they want to answer. So Pete just calls back to the police officer, asks what do you want to be answered, to have answered. And he states 3 main questions. The first one is, can you reconstruct events? The second one is, can you get the report? Because I guess that they tried it too and weren't so successful. And this third one is kind of specific. Did the vehicle accelerate by itself? It's interesting because if we think what the police officer said, he told us that the driver was parking automatically and the vehicle accelerated afterwards and fell down the hill. So I suspect that someone must have stated that the vehicle did it by itself and not the driver, so whose fault was it? But we obviously did some forensic stuff up to this point, so we already got the report, so green check mark on there, awesome. So let's look at the first question again. So how can we reconstruct the events? Well, let's just dive into the report itself. So here's a screenshot from the actual report. You usually get such tables where different events are presented, and this is an event. It's only one event for the ECU we are dealing with, but this event we have some information regarding the service brake, stability control, ABS activity. You can read the timetable here in the following way. -5 is 5 seconds before the event occurred, and 0 is actually the time of the event. So airbag ECUs, sorry. Airbag ECUs usually implement a sliding window of 5 seconds where they're always storing this information. So can anyone spot anything interesting right here? So we have some ABS activity, everything is off, so no ABS was engaged. We have stability control, which is, I guess, everything when you're drifting, for example, that the stability is working. And service brake. It's weird. What is service brake standing for? Luckily, also those reports state some information on the wording we have here. So let's check what actually is service brake. And it's pretty interesting. Because right here we can see that if the service brake is on, the pedal was being applied by the driver. And if the service brake is off, the pedal was not applied by the driver. In this case of the report, the service brake is off. So the brake was not pressed. So if you suspect that your vehicle is driving down a hill by itself, well, I think most of us would obviously try to brake, right? To not get hurt. But this is odd because the report here says that the service brake was off and therefore not being applied by the driver. Well, okay, just note it down for report purposes afterwards, and let's get to another event, but we need to note it. The next table is all regarding the vehicle speed, accelerator pedal, and also the RPM, which is how fast the motor is spinning. And there again, you can read it in the same way, 5 seconds before the event, 0 is here at the event. So what can we spot here which is interesting? Here in the vehicle speed, we can see that the vehicle speed is somewhat the same and then increasing. So right before the event, we have the vehicle speed of like 13, 14, 18, 22 and 26 kilometers per hour, which is pretty fast in a parking state. And mapped to this, the accelerator pedal, so the pedal of your gas pedal, how deep it got pushed into, we can see that approximately at 4 seconds before the event, it got pushed even harder. 14, then 16, then 17, then 18, then 20, 24, and even at the end, 0.5 seconds approximately before the event, the accelerator pedal was pressed with 100%. This is pretty odd, and also the shift is pretty odd. But if we look at vehicles, we can also see that if you press the gas pedal, the gas is not applied directly, so there's also a delay. So this would, for example, stand for the delay we can see right here. So just without any interpretation, just state what we can see here. So we have increasing vehicle speed, and the accelerator pedal was pressed harder and harder up to the actual crash. This is weird, right? So just summarize it again. So the brake was not pressed. The vehicle speed was increasing all the time up to the event. And the accelerator pedal was pressed harder. And the question here is, what could have happened? And this is something we obviously need not to answer, because as an investigator, we only presenting the results. The interpretation is, for example, done in front of court. But Pete and myself were so interested in this case that we asked the insurance company, the police, and the police, how could you interpret such weird data? And we got interesting results. So they told us that this behavior is pretty obvious or pretty normal in cases where someone is mistaking the gas pedal with the brake, or the brake with the gas pedal. So this is obvious, because let's say if I would phrase that this behavior with the gas pedal pressed even harder, I would try it with a brake if I'm right before an accident. So maybe the driver has mistaken it. So let's jump back to the question. So green checkmark is, can you reconstruct the event? We showed what happened without interpretation. So brake was not pressed, vehicle speed was increasing, and the accelerator pedal was pressed harder. And the next question was, did the vehicle accelerate by itself? So in Tesla vehicles, we have the function of an autopilot. And the autopilot is also responsible for automatic parking purposes. So what we need here, because the airbag ECU didn't give us any information regarding the autopilot or logs regarding the autopilot, we need information from the autopilot itself. Examples could be an autopilot dump or logs from the autopilot. If there are any logs, we don't know. So just ask back to the police, but sadly, they cannot give us access to the autopilot logs. They just tell us, due to intellectual property circumstances and no access to the vehicle anymore, we can't get autopilot logs. That's bad, because we can only answer then 2 questions. We were able to reconstruct the events, and we were able to get a report. But we can't answer the question if the vehicle accelerated by itself based on the evidence we collected. So let's check back on the open questions, because I said before that data integrity isn't given in automotive forensics or components. So is EDR data even trustworthy? Can we trust this information that, for example, the service brake flag was off? Or maybe it changed due to the circumstances the vehicle was in? We can't answer this. And also, sadly, access to evidence we really needed was not given, so we weren't able to solve the case as a whole and all the questions. And also, we didn't perform any correlation of different data sources. We just got the airbag ECU, so we can only get information from the airbag ECU. No information from the back end, no information from the smartphone, no information from the autopilot, so no correlation for us. And also no validation, because if we would do correlation, we could also validate the results from other devices. Say that 3 devices say that the specific vehicle speed was approximately 20 and one device says no, it's only 5. Then we could state that the vehicle speed was maybe 20 because more devices tell us that it's 20. And what we really need to change, and where we really need new proposals in automotive forensics, are generalized approaches, because we already saw at the beginning that vehicles are complex. So we need something generalized. The data needs to be normalized, because as we saw, we needed the backend, so as a Tesla's backend, in order to get us the report. We weren't able to interpret it on our own. The data was not normalized. So the correlation is even harder, because we just have a weird PDF file, so no correlation. And we need new and better tools. Those tools shouldn't be proprietary and vehicle dependent or manufacturer dependent. This needs to be something independent. You can't buy tools for 20,000 euros for one specific case, for example, on a BMW, and then another 40,000 euros for a case on a Tesla here. So we need new and better tools that are adaptable to other manufacturer, other models. And we need to view the vehicle and the ecosystem as a whole. Not only the vehicle, also in-vehicle files, also the ecosystem. And this is what I'm trying to do with my work. And this is what I'm doing, not trying to do. This is what I'm doing with my research on automotive forensics. I hope you really like this tutorial. Thank you so much for participating.